This is a video on empirical molecular formulas. This should be the end of your note packet, the last thing you're doing. And empirical molecular formulas go together. They're really kind of the same topic, but we just deal with them in slightly different ways. So the first problem is an empirical formula. And what you're trying to figure out is you're trying to figure out mathematically the simplest ratio between the different elements. So, for example, are they a 1-to-1 ratio? Are they a 1-to-2 ratio? And the reason why this is helpful or it's useful is because if you know the ratio, then it's pretty easy to tell what chemical it is or what formula it would be. So it's just a useful thing for identification. It's a useful thing for predicting properties and that kind of stuff. But instead of like looking up your formula on a blue sheet or the periodic table or organically, you actually use math to figure out the ratio. And again, this is the smallest, so it's the simplest ratio we have. So there's a little rhyme that you can use to remember how to do empirical formulas, and you always do the same steps for an empirical formula, so it's a very linear, straight fashion. So the rhyme is you do percent to mass, mass to mole, divide by small, and then you multiply till whole. You don't always have to do the first step, because if you're already in mass, then it's an unnecessary step. Excuse me, and you don't always have to do the last step because sometimes, most of the times, I would say that it's already a whole number, so it's also an unnecessary step. But these are the four steps that if you always go through them and you make sure you do them, then your empirical formula should be good. So what we're going to do is do two empirical formulas, one molecular formula, and then we'll practice some more in class. All right, so this is what an empirical formula question looks like, and they say they're going to ask you either for specifically the empirical formula, or they could also ask you for the simplest formula because they're interchangeable with each other. So they have a 2.5 gram sample, and somehow they ripped that apart, and they found out that they had 0.9 grams of calcium, and they had 1.6 grams of chlorine. So that's your first step. So if you think back to our little rhyme, the first step in it is percent to mass. In this problem, that's unnecessary because we are already in mass. Like we know we have 0.9 grams of calcium and we have 1.6 grams of chlorine. So we don't have to do that. And if we look at the next step, what we're going to do is we're just going to do a mole conversion, and we're going to go from mass to mole. So over here, what I did is I took my grams, I looked up the molar mass in the periodic table, and I just divided them to go from mass to moles, and I got my moles of both the different things. Now notice I did the correct sig figs. I had 3 sig figs for calcium, so that's how many I have in my moles. I had 4 sig figs for chlorine, so I have 4 sig figs in my mole. And that can become important in empirical formulas so that you get the right ratio. So looking back at our rhyme, we didn't have to do percent to mass. We did mass to mole. And now what we're going to do is called divide by small. So what we're going to do is we're going to look at these mole values, and we're going to say which one is the smallest value. And obviously 0.0224 is smaller than 0.04507 as a number. So what we're going to do is we're going to divide both of them by that number. So what I did here is I took calcium, it's divided by itself. So obviously that's 1. And when you do chlorine, you get approximately 2. And it's not exactly 2. Let me actually calculate it quick so I can give it to you. Divided by 0.0224. It's 2.01205, blah, 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 blah. As long as you are very, very, very close to a whole number, you can just round it off. Ones that wouldn't be a whole number, one like a half, 0.6, 0.7, that kind of stuff. This is exactly 2.01. I mean, that's pretty darn close to a whole number. The very last step, then, what we need to do is say multiply till whole. So this step would be if these two numbers right here were not whole numbers. So like maybe we had a 1 and a 1.5. 1.5 is not a whole number. That's when we would do that step. We'll actually practice one of those together in class. But right now this is unnecessary. So we have our simplest ratio, 1 calcium for every 2 chlorines. And what that means is we don't have to do that last step. And the empirical formula would be CaCl2, because 1 calcium for 2 chlorines. If you get your ratios after you've done the divide by small step, and they're not whole numbers, like for example here, this is where you have to multiply by something. And I said for right now, don't really worry about it. We'll do more of this together, but it does happen where the simplest whole ratio is a little more than what you have to do. So be aware it can happen. But most of the time when you do empirical formulas, you should get a nice whole number for it. All right, so this is just another empirical formula. We have, we want to determine the empirical formula for an iron oxide that's 78% iron. So the first thing you have to just be okay with is that if we have 78% iron, we have to have 22% oxygen, just from a 100% perspective. And if you think back to our rhyme, we are going to have to do the first step. So it says you have to turn your percents to mass. The easiest way to do that is assume you have a 100-gram sample. If I have a 100-gram sample, 78% of that is 78 grams. And if I have a 100-gram sample, 22% of that is 22 grams. So that makes it much easier. And then when you do that, you can very easily say, oh, instead of 78%, I can just pretend it's 78 grams. You could assume anything. You could assume you have 6.78 grams of your sample. Then you would just have to figure out what's 78% of that and what's 22% of that. I just try and make the math simple. So once you have your percent to mass, you're going to see here you do your mole ratio. So we divide it by the molar mass, divided by the molar mass. We got our moles, and you can see they're exactly the same. So when you divide by small, in this case it doesn't really matter which one you divide by because they're exactly the same. And what you're seeing is the ratio is a 1-to-1 ratio. Those are both whole numbers. So that's our multiply of whole, they're already whole. So what that's telling us is this is FeO, and it means that it's iron 2 oxide, not iron 3 oxide. So these are how you do empirical formulas. These are the normal steps for empirical formulas. And again, as long as you follow that rhyme and you follow the steps and you do them in sequence, empirical formulas are very straightforward. If you don't have it written down, if you don't practice these, they can just get hard because there's steps to them that you have to get used to. Last thing for today is molecular formulas. And basically, molecular formulas is empirical formulas with one more step. And what a molecular formula says is that sometimes the simplest ratio isn't what really occurs. So the classic example of this is benzene. If I had you do an empirical formula on benzene, you would get a 1-to-1 ratio. So you would get 1 carbon to 1 hydrogen. That's not really what exists. What really exists is a C6H6 molecule. So a molecular formula is the number of atoms that actually occur. What it means is you do your empirical formula and you do an extra step. And there's typically 2 ways that they do an empirical molecular formula. I'll show you the trickier way and we'll talk about the other way. So we say we want to find the molecular formula. So they're telling us that. We have 42.5 grams of palladium, which is an element you don't see very much, but we have some. And we have 0.8 grams of hydrogen. And if they're giving you molecular formula, they're going to have to give you something else. So they said in another analysis, it was determined that the molar mass of the compound is 216.88. So we'll come back to that at the end, but we just kind of proceed like normal. So the first thing we're going to do, we don't have to go percent to mass because we're already in mass. So the first thing we're going to do is convert from grams to moles. And you can see we took our 42.5 grams of palladium. I looked up my molar mass on the periodic table of palladium, divided it out to get my moles, and again, sig figs. For hydrogen, same thing. I have 0.80 grams of it, divide it by the molar mass from the periodic table, and I got my moles. Next thing is when you divide by small. So you can see here, again, palladium is the smaller one, 0.399 is smaller than 0.8. So 0.399 divided by 0.399 is 1. And again, the second one's not perfect. 0.8 divided by 0.399 is exactly 2.0050. Since it's so close, even with sig figs, it's 2.0, we can just round it exactly to 2. These are both whole numbers, so 1 palladium, 2 hydrogen, and then for our empirical formula, we're done. That is our empirical formula. But in this case, they asked us to do an extra step, And what they gave us for that is they told us the molar mass. So what it's telling us is the molar mass of our formula has to equal that. So what we're going to do is we're going to check that. And what you can see is what I did is I looked up how much palladium weighs. One palladium is 106.4. I looked up how much hydrogen weighs. 2 times 1 is 2. I added it together, and my empirical formula's molar mass is 108.4. And that's a little concerning since the molar mass is 216.88. So what we have to do is we have to do a thing to figure out what we need to multiply it by. If like this would have matched, like if the 108.4 matched what they would have told us, all that means is that the empirical and the molecular formula are the same, and that's just nice because it's easier. This case they're not, so we have to do an extra step. So what we do, oh, I don't know why it's like taking me backwards. Here we go, hopefully. What I did is I took the molar mass that they told me. So this 216.88 is from the problem. They said this is what the molar mass should be. I divided it by the molar mass that I got from my empirical formula. And again, it's not perfect, but 216.88 divided by 108.4 is 2.0007, which is effectively 2. So what that means is that my empirical formula is off by a factor of 2. So what you do is you take your empirical formula and you multiply everything by 2. So instead of having 1 palladium, I have 2. Instead of having 2 hydrogens, I have 4. And then that's your molecular formula. Empirical molecular formulas aren't that impossible or anything, but you do need to practice them just because you have to get used to the process that they're giving you. So hopefully this helps. If not, please come and see me so that we can make sure that you get this, that you're understanding it.